Sorry, I forgot to.
Hi, can you hear me now?
Oh,
But there is the microphone on. Wait.
Yeah.
Okay, does it work? No, there is still some.
On the top row button.
Okay.
Yeah.
No, but I still hear myself, although it is muted. Maybe it's some other laptop.
What's going on?
I'm hearing from Benjamin. Yeah. No, this is
Test.
test. But I still hear myself.
Is some audio coming from where? Test.
Okay, okay.
But is the room still? Can you say something?
Yes. Can you hear me? Does this work? Yes.
Yeah. Okay.
Okay. Good.
Okay. Good.
Yes.
Online people, can you hear us? Okay. Sorry about it.
Okay. So Benjamin introduced many of the ingredients of the functional normalization group. So we have our recipe, we have our ingredients. Now we can try to actually apply that to a simple case that can more or less be derived within 1.5 hours, which is the Einstein-Hilbert case, where we only have two couplings, so things are relatively simple. But now to recap, let's now write here the differential question, big enough just to recap all of the ingredients that it has. So here we have a variation of the effective average action, which in general can depend on a bunch of fields. And here we have 1/2 super trace of the modified inverse propagator. So we have our effective average action here, second variation in general with respect to every field that you have in your theory. And this must be regularized by a regulator term, inverted, multiplied by the variation of the regulator, and that's it. So now, what are the steps to solve this equation? Of course, as Benjamin mentioned a couple of times, this equation cannot be solved exactly. So one has to rely on some approximations. So in practice, what one has to do is to first start from an ansatz for the action. And the simplest possible ansatz is Einstein-Hilbert, since it only has two interaction couplings, gravity. So in general, so step 0 is to choose, I think this one does not really work properly. Yeah. Step 0, this works. We need to choose an ansatz for the action. An ansatz, that means just the physical part of the action, for instance, Einstein-Hilbert, but then that has to be complemented with some more ingredients that are the gauge fixing. Because this here is a gauge symmetry, diffeomorphism symmetry, which needs to be gauge fixed. So we have our action gamma k plus a gauge fixing term, and once we add a gauge fixing term in the path integral, and therefore in the flow equation, we also need to complement this with the cost action. And ideally, one should first try to understand the structure of the field content that one has. So whether there are interactions, non-minimal interactions between couplings to understand what happens in there. And in particular, all of these, within all of these, as Benjamin explained in the last part of his last lecture, we typically use in gauge theories the background field method. The background field method, and in particular in the following, I'm going to use a linear split for the metric. And as Benny said, one can use different ones, but then it gets more complicated. So the metric G mu will be a background metric plus fluctuations. And what does that practically mean? It means that one expands the action and therefore also the second variation around this background. And in order to compute this, we need to have the second order form of the action in the fluctuation field. And while this is just a method, background field method, on top of the method itself, so splitting the metric in background plus fluctuations on top, that then are those we integrate over in the path integral, we need to make an approximation in the sense that once an ansatz plus background field method is applied to the action, and once variations are computed, we evaluate everything at 0 fluctuations. So it means that for the gravitational sector, we would have here H equal to 0, but also the gauss field, as we will see in a bit. So all the fluctuation fields after variations are taken are set to 0. This is the starting point. So once we have ansatz and we understand how to parameterize fluctuations, we need to compute these two parts of the equations, the left-hand side and the right-hand side. Let me still use the black. So the left-hand side, you can leave it as the last step because it's very straightforward to compute. You just take your action where now the couplings will be functions of the renormalization group scale and apply your KdK derivative, the derivative with respect to the renormalization group time. The tricky bit that takes to people, even months, depending on the system one works on, the right-hand side. And this can involve several steps. It can be arbitrarily complicated depending on the number of fields that one has in the theory, how they are coupled to each other, because if they are coupled minimally, this guy gets complicated and one has to invert that. So how do we proceed with this? What is the first thing that one should do is to expand the effective action, the effective action about G bar, okay? So this would be my first step, and regularize this. So this would be for the right-hand side, the step one. So compute the regularized gamma 2. Second step is to invert. This is the second step. And this is essentially the computation of the propagator, so one, the modified inverse propagator. Let's call this step inversion. Step 3, just multiply these two terms, so the KdK with the modified inverse propagator. And this is independent of what is the content of your theory. It's just might take some computational time, but there is no conceptual problem in there. And finally, one has to compute the super trace using the kernel techniques that Benjamin talked about. And practically, just to recap what this leads to, after you have to compute this bracket, you have essentially a function that depends on the Laplacian, ideally. Then there could be some open derivatives, but we try to avoid them. And out of this function, so you would like to compute the 1/2 of the super trace of these functions of the Laplacian that I will call delta. And this is the sum of, in principle, many terms, okay? And the lowest order ones are the following. So we have 1/2. Now I'm specializing to d equal to 4, but I may compute the stuff in general dimensions. And here we have a space-time integral. For now with a general metric. And we have here also 1/2 and a first integral with z and w of z, and another term which is r/6 for scalars. Then there might be extra terms in case one is tracing over different types of fields. And here we have another integral with here w of z. And in principle, one can also have higher order terms in the derivative. And remember that then all of this has to be computed on the background. So at some point here, we will specialize to the background metric after variation have been taken, and this will be the background curvature. And in principle, what one would need for special, for more for better truncations, one would also need higher derivative terms. But in practice, then to extract the beta functions, since we will be starting from Einstein-Hilbert, so from on the left-hand side here, we will have just the Einstein-Hilbert term. That means terms up to linear order in the Ricci scalar. So this type of these two integrals that are called threshold integrals are everything that we need. So these are called threshold integrals. In principle, they depend on the regulator because this enters in both of the factors inside the bracket. And okay, at this point, I believe we have all of the ingredients there. So I will just keep this whiteboard like this all the time. I try to erase the stuff that stop me from doing that. And that will be our reminder for all of these steps. Yes.
Sorry, so the integrals over z are threshold integrals?
Yes.
Okay.
Yes.
Mm-hmm.
And in the end, what will come out of there is functions of decouplings. And of course, I forgot to say another small steps here is that either at the beginning or at the end of the calculations, one needs to replace decouplings with their dimensionless version. Okay, so that is essentially the general strategy. The super trace can get complicated, but for Einstein-Hilbert, we only need the first two terms. So, okay, let's now start with the case of Einstein-Hilbert. And technically we call this truncation because in principle we need also higher derivative operators in the action, but we are just using one specific expansion scheme. For instance, the derivative expansion in derivatives and truncating to a certain order, expansion order. In this case, Einstein-Hilbert is to second order in derivatives. So here we have this space-time integral metric, and because of the Euclidean singulator, this has a positive sign and this has a negative sign, and then 16 pi gk. And this is just the physical part of our action. And this now has to be complemented with gauge fixing and ghost term. Okay, that essentially are have been introduced by Luca in his lectures. And of course, gauge fixing is important because you have a question?
Yeah, so since you include cosmological constants, so is it your background?
My background will be generic. I mean, of course, in more extensive truncations, so when you include higher derivative terms, sometimes it can be useful to specialize, for instance, to Minkowski background. Okay. For instance, because if you want to avoid the mess of the heat kernel when you have a lot of higher derivative terms, then you could, in principle, just expand about Minkowski, and then your heat kernel, your threshold integrals will turn into easy, not easy, but more straightforward momentum integrals. Yes.
My question is maybe very basic. So you start with the effective action, which is the
Yes.
cosmological constant, so you have physical. If you press all the equations.
Yes,
the
but
solution is
the background doesn't need to be the solution to the field equations. So what has been shown in the context of scalar field theories is that if you expand about the vacuum expectation value, for instance, of the field, you have a faster convergence of the results, but it is not necessary to get to the results. So it means that you have to work a little bit harder. But in general, the background doesn't need to be a solution to the field equation. It's general. It's just you are just performing the functional integral. So if you're doing that exactly, the results should not depend on the background you expand about. Okay, and that's why in the simple truncation we can leave it generic, and therefore it's useful to do that. Yes.
How important is cosmological constant? Can you remove it, or it is essential to it?
I mean, you could, but I think it doesn't really give any problem. And also, technically, it is the first order term. So you're, to be consistent, you should either have like a cosmological constant without R, or if you go to the first order in R in this curvature expansion, then you have to keep the zeroth order term, right? Okay. And at this point, so we need to add the gauge fixing and those term. So the gauge fixing is simply given by 1/2 and d for x square root of g bar, because now I'm expanding on the background, general background metric, and f mu g bar mu and f nu. And these, let me now just do this properly. This should be mathcal f mu. I don't know how to call this. It's like a calligraphic, okay? H rho sigma, and here we have the square root of 16 pi g, which now depends on k. So also here it has to depend on k, and alpha, which is the gauge fixing parameter, and here we have this we have here the covariant derivative on the background, and this product is symmetrized. We have sigma and rho here, minus yet another gauge fixing parameter beta, and g bar rho sigma d mu, and here we have h rho sigma. Yes. Okay. So we are letting the GK flow with the RG. Does it mean that the Planck mass does it flow too? If so, what is the physical meaning of this? So the physical Planck mass does not run. But it is important to let this run with respect to the renormalization group scale, because this allows us to verify whether the theory has a well-defined continuum limit. In practice, as we then go to k equal to 0, it will turn out that gk corresponds to a relevant parameter, so we can fix it by experiments. And we can just make it coinciding with the Newton coupling that we observe. Yeah, so in the end, at the level of the effective action, the Newton coupling will be fixed. And so it will be at the level of the scattering amplitude. So the physical Newton coupling, the physical Planck mass does not run. And I don't think there are other questions. Okay, thanks. Okay.
What's coming square bracket?
Here, oh, sorry. Here I missed probably one. Yes, there is one more missing. Sorry. It's just the Renegade data. Okay, and then we have this term. So the notation is probably slightly different than the notation that Luca used. So I think he used here a unique parameter for 1 plus beta. It's the same, obviously. And we also have this alpha here. I should also mention that in general, one could let these two gauge fixing parameters run. So that we could let these be functions of k to see if they themselves have preferred fixed point values. And it turns out that the Landau gauge that corresponds to alpha that goes to 0 is a fixed point of the flowing gauge fixing parameters. So some people think this might be a preferred gauge fixing, but we are not going to use this. It's called lambda limit. We are not going to use this. Actually, what we will use, and what is used many times, is the harmonic J gauge, and you will see soon why. Where alpha is equal to beta equal to 1. And this simplifies stuff quite a bit, especially for the inversion. Yeah.
If we run that alpha run to 0, don't we get a 0 on the denominator? So a problem?
And so the point is that one should keep it there and then send it to 0 at the end of the calculations, and then it doesn't lead to problems.
Yeah.
Other questions?
On Zoom.
No fluctuation field to 0. Oh yeah, sorry. Why are we taking the vanishing fluctuation field? Don't we lose information about the dynamics of H in this way? What are the consequences of this? So we are not really taking it to 0 from the beginning, otherwise we kill gravity. But what we are doing is to take variations with respect to the field and setting it to 0 afterwards. That is equivalent to take the second derivative of a function. Okay. Gauge fixing, ghost. And for ghost, in general, we have a dependence on the full covariant derivative, but I'm going to specialize immediately and set it to the background covariant derivative, such that we have immediately a structure which is quadratic in the fluctuation fields. And this, I didn't say that, but it's much more clean to structure our parts of the action as field. Now, not in general, not for gravity, but in general, structure the things as phi and then some operator evaluated on the background phi, so that then when we are going to extract the gamma 2, we have it already there. And this, of course, has to be evaluated on the background, and then the fluctuations are set to 0 after we remove the fields. So once this is done, our ghost action reduces to 1/16 pi gk alpha, because of course it is obtained by taking the Lie derivative along the ghost field of the gauge fixing action roughly. And here we have our usual space-time integral evaluated at G bar and anti-ghost field. And then we have a structure of this type. So we have V square delta mu alpha plus 1 minus beta over 2. And here we have open derivatives and Ricci tensor. So something like this. Oops, and there is no space for the poor the poor gauss field who gets to go to the second line. And yes, and here we have our ghost action with anti-ghost and ghost vector fields. And from here already you can structurally see that there will be some simplifications for the harmonic gauge, because if I set beta to 1, this term vanishes. And this is pretty important. It's not just a random term, it is a random term with open derivatives. So derivatives that are not contracted together, because derivatives contracted together give rise to a Laplacian. Laplacian is nice because we can use directly the formula used by derived by Benny. If we have this type of structure, the inversion starts to get more complicated. So harmonic gauge is a good thing. Okay, and on top of this standard complementary action, the gauge fixing and the ghost, we need to now regularize our theory. Okay. Indeed, to derive the vector equation, what one does is to modify the path integral to regularize it by adding an action, a regulator action, which is structurally quadratic, once again in the fluctuation fields, which is good because then it is easy to just have everything in terms of this structure, and with a regulator. And in this case, now we have the fluctuation of the metric, so H, and we have this ghost, ghost, and therefore we need the regulator action to be added to the full action to contain both a regulator term for the ghost and the regulator term for H, for the graviton fluctuations. And I'll place it here. I hope there is enough space for this. And we have this S delta Sk, which is 1/2, our usual 1/2. And G bar. Now, for the graviton, of course, it is a spin-to field, and this means that the regulator will have 4 indices. So for the graviton, it is mu nu sigma rho, and here we have H sigma rho, and something similar for the ghost part of the action. Here we have C bar mu, and RK for the ghost, particle ghost, mu nu, and C. And now we have essentially everything that goes inside the effective average action. So what do we do next? We need to understand the structure of the Hessian, so the second variation of delta, of gamma, with respect to the fields that we have. And let's do this here. Let's understand the structure.
There is another question on Zoom.
Yes. So sorry to bring this up again, but taking the limit h that goes to 0 in the left-hand side seems like a non-trivial approximation, since we neglect terms that could potentially run, right? So what we do in the left-hand side is a trivial expansion, in the sense that since there is no variation in the left-hand side, everything is evaluated on the background. So yeah, you would only have essentially the physical part of the action that contributes to the left-hand side, but this is normal. Mhm.
Also, a question about the gauge. So harmonic gauges, I see how beta equals 1 simplifies this
Yes,
somehow, but alpha equals 1 is simplifies somewhere.
yes, but we will see that later. So it simplifies a lot the structure of the second variation for the graviton part.
Okay.
And so it will be clear later. Okay, structure. So we go to the right-hand side. And can you see this well? Indeed. Probably the one that was working while I left it there on the table. Right-hand side. And here, though, what do we have exactly? So we have here our 1/2 super trace. And what we have here exactly to invert in principle is a 3x3 matrix, because we have 3 entries for the fields. We have the H, the graviton fluctuation, we have the C and the C bar. So for instance, here we would have as a first entry the variation, the second variation of gamma k with respect to H. Here we would have second variation of gamma k with respect to C bar, and the same here, like C and C. And just let me write what else one would have here. Here we would have H C bar, yes, and H C bar C. I'm not writing the variation, it's just to have an idea structurally how this looks like. And this is to be multiplied by the regulator, which is once again a matrix. So here we have, sorry, I forgot. Here there is the variation with respect to k, and then our regulator term. We have the regulator part of the graviton fluctuations. So here we have R k for H, and then 0, 0, 0, 0. 0, 0, and RK for C, which is of diagonal. It's not diagonal because here the structure of the ghost action is such that we have C bar C. So the kinetic term, the p squared that we need to regularize, is actually here in these two terms. And therefore, the regulator, so the scale-dependent mass term that has to take care of fluctuating modes must be of shell as well. So here we have this structure here. And this helps us, let's just make close this. This helps us because essentially, especially after I already wrote the ghost action in this nice form, so on the background, the graviton part and the ghost part are kind of decoupled. So especially considering it here, then we have to take the background field approximation, so setting after we have taken the variation H equal to C bar equal to C equal to 0. So only the quadratic terms in the fluctuation fields will contribute, and this means that practically at the quadratic order, gravity and the Faddeev-Popov ghost, as should be, they are decoupled, and therefore this is approximately equal to 1/2 super trace of the graviton part. So here we have the second derivative of gamma k with respect to h, regulated, of course. And here, of course, remember that this is a kind of an abstract notation, but these are objects with indices. So these are for indices, these are for indices for the graviton part. And then we have essentially twice the contribution from ghost because they are symmetric, and therefore the two cancels out. And what we get out is just the super trace of the ghost part, which is a second variation of gamma k with respect to c bar c, regulated and inverted, times the regulator part for divided of ghost. Okay, so this means that instead, and this helps because if H would be badly coupled with the ghost or with another field, if one then has to invert stuff that is coupled together, the inversion also involves the use of some inversion formulas for block matrices. And here we can essentially avoid this because stuff is decoupled, which is useful. And therefore, it means that we can just compute the contribution of the traces from different fields independently. They are just the sum of the contribution from different fields. And now we can proceed and compute these contributions individually. So this is the, let me call this the right-hand side coming from the graviton, and this is the right-hand side part that comes from divided of ghost, so just GH is enough. Let's start from the right-hand side coming from the ghost because it's kind of easier than gravity. Yes, and because now you see that the ghost action structurally has already the right form, so it has the structure phi something and phi, so field sandwich stuff field. And as I mentioned already, this type of open derivative terms make things more complicated. So what we are going to do is just to set beta equal to 1, such that practically with beta equal to 1, but let me first write that here we are going to compute the right-hand side for ghost. And now the ghost action for beta equal to 1 has this form. So it is 16 pi gk alpha, that for now we'll just keep it there. And then d for x square root of g bar. And then here we have something like this. So let's call this W for ghost. And this is a function of delta bar C nu. And this has a nice structure. This can be written as minus delta bar. So this is essentially the just delta without the minus sign is minus yes, minus g mu d mu d nu. evaluated on the background, and this essentially comes from this part. And here we have an identity plus a term that we can call Rit on it is essentially the Ricci tensor evaluated on the background. And here to make the indices match, we have mu and rho. And we like this because this is a function of delta bar, and therefore it is the perfect ingredient to give us a meal for the it kernel machinery. And in particular, it has the structure of delta, well, modulo and minus sign, plus an endomorphism. So practically, what this means is that we can regularize this, and also there are no open derivatives. So we can regularize this term by taking all of these as the entry for our regulator. This has to do with how one practically implements the regulators when computing the flow. Practically what one does typically is to use mathematical computer algebra in order to compute the flow, especially when things are more complicated than Einstein-Hilbert. And therefore the regularization of the right hand side, of the Hessian can be seen as you can think of it as a replacement rule. So every time that you have an iteration of a delta bar, which is essentially on the flat space, this would be our momentum that we need to regularize with something like k square, which takes care of the step-by-step integration of momentum. Yes.
So plus p squared or minus p squared?
I think. So wait, this should be. I understood this camera. Wait, this should be okay. Plus, yes, because essentially every derivative would be replaced with I p p mu. So there is another minus sign that compensates for that. And we have a mass term, so a regulator for essentially each iteration of the regulator term. So one way of implementing this in practice, and this is roughly called the type 1 regularization, is to replace each kinetic term with corresponding regulator that depends on delta. So one is regularizing the delta itself. And another way, the type 2, is to replace delta when there is, well, here there can also be like an endomorphism in general, and still we would have something like this, I forgot. But we can also have a regularization that takes into account the endomorphism just at the inside of the regulator. It shouldn't really matter what we how we implement the regularization in the end. So physical quantities should be independent of this. But the type 2 regularization is particularly useful when applying the heat kernel techniques, because then we have one single argument that goes inside the heat kernel function. And if instead we want to do something like this, then there is one extra step, namely that you remember that Benjamin showed to you that this heat kernel function can be expanded as an integral running over s of e2 minus s delta, right? And if you have this exponential with something like this, the kernel essentially acts on works for this delta and this delta bar, which is our s, and we would have an e left over in the exponential that we need to expand about equal to 0. So we would have an additional series essentially, and they give the same results, but it's just more is more steps to get to the results. So I would just use this type of regularization. And another thing is that with this type of replacement that you can think of, you are automatically doing the following. So you are taking into account here that the regulator has the same prefactors that you see in essentially all parts of the action. So for instance, these factors 1/16 pi g. And this is not necessary, but very useful, because at the level of the flow equation, these factors will appear both in the regulator kdk rk, but also in the denominator that comes from the propagator. So these denominators will cancel out if one implements them in all parts of the action. So after this, then we can essentially write down the regulated part, the regulator part as minus, so same prefactor as for the action, square root of alpha, sorry, should be the same prefactor as for the cost action. So yes, is 16 pi gk, and then space-time integral, and we have c bar mu, and then our regulator term for the ghost that depends on delta bar plus r, and this would be like mu nu c nu. Then one can sum things up together. So now we have, if you sum this part with the ghost action, in total one has a function of delta bar of the Laplacian, which one can insert as an input with in the heat kernel formulas. And what this gives rise to is the following. Let me write this down here. So now the right hand side for the ghost, after one has evaluated the trace, is something like this: 1 minus 16 pi square before x g bar. And now we have 4. And here we have the first integral that comes from the heat kernel formula, okay, it's z, and we have the first z, which I think in the original formula depends on the d is something like d over 2 minus 1. And then what comes out here is kdk regulator r kc of z. And here I'm leaving the regulator as unspecified. At some point, one can say, I take the leading regulator, or I take an exponential regulator, and this is how and when one can compute, actually compute the threshold and the integrals. Minus 1 over alpha k dk gk alpha. And here we have again rk c of z over z plus rk c z. And then the second contribution to the heat kernel formula, that is 5 over 3 r bar. So this is literally the second term in the expansion about r bar equal to 0. And we have our second integral. So again, an integral in z. This time it's essentially the same, but without the z. So we have k dk rk c z minus 1 over 2k dk gk alpha. Okay. Oops. Z over Z plus RK C Z. And here it is not really useful to derive things because it's just using the formula and summing things. But I want to tell you like where the different things come from. So the Z is stands for the kinetic term plus R. This is where it comes from, plus the regulator. So this is literally what in the flow equation is gamma K2 plus R. This is where it comes from. And this part instead is the K dk R K. And why there is also this G, because we have inserted the G in the regulator. Okay, so when we derive this stuff with respect to K, we obtain a contribution that has the variation of G. And there would be also like a denominator that depends on essentially 1 over GK, but they cancel out between the numerator and the denominator. So they drop out. How much time do I have? Like 30 minutes.
40.
40, okay, that's fine. This is the easy part. Okay, you have a question?
Yes, sorry. So the runnings of this alpha, the gauge parameter and G couple.
So I said I'm in this calculation alpha is fixed, so it's not running.
Oh, okay.
Okay, it's an approximation where it doesn't run. So yes, I mean this essentially is the variation of GK. Alpha is not included, but it's just they come together because of this is the term where
Yes.
they come from.
And this is how they determine that alpha equals 1 is a fixed point of this flow, or?
So alpha is equal to 0 is a fixed point
Oh,
of the
zero,
flow,
sorry.
but in order to see that, you need alpha to run. So it is not. So in this case, it is not possible to see this. But we will see something else instead that with alpha equal to 1, things simplify.
Sure.
Instead, if alpha goes to 0, things do not simplify, but it might be better in the sense that the flow equation would suggest alpha equal to 0 as a fixed point, gauge fixing the parameter, fixed value. Yeah. Okay. So now we have the right-hand side for the ghost, and one thing that you may observe already is that once you specify your regulator, and once one switches to dimensionless G, the structure of the right-hand side, just structurally, is a function, let me call it maybe F1, that depends on the small gk, and in principle, like in generic calculation, can depend also on other couplings, plus R bar, another function that depends on, again, gk, in principle, other couplings. And these, I think I forgot, here, okay, here I have the space-time integral. There should be a space-time integral here as well to match with the left-hand side. So once we will compute the right-hand side for the graviton part, there will be a structure that is exactly like this. So we can sum those functions and then compare with the left-hand side, and then we can compare essentially the term that have the same order in the expansion about R bar equal to 0. So in our curvature expansion of the action, and this will be called the projection of the flow, because you project like in along some axis, and you can extract the beta functions. So left and right hand side for the ghost is done. We don't need the structure anymore. So now we can go into the right hand side for the graviton, where we don't have time to see everything, but we can at least see why alpha equal to 1 is convenient. Because now for the right hand side, for the graviton, let me call that H. Well, there are some more steps in between because for the ghost, you see, the structure was already our sandwich field, operator field. In the case of the graviton, one has to expand about G bar in powers of H, express that in second order in H. There can be also some partial integrations to do just to bring it to this form, like H, some stuff H. So there are some steps more that I don't have time to show, but they are written somewhat detailed in the lecture notes. And yes, so how this looks like, the quadratic part for now, just the quadratic part for H, something like this, 32 pi gk, and then our usual spacetime integral. After the steps I told you about, here we have our sandwich with within the two fields, the graviton fluctuations, so that looks like this. So we have our Laplacian minus 2 lambda k plus 2 over 3 r bar, and this essentially comes just with the identity sigma rho, or the sigma in the notes. Then we have the background while tensor, mu rho mu sigma, and here we have another operator which is of this form. So it has 1 plus beta square over 8 alpha Laplacian, background Laplacian, minus lambda k plus 1 over 6 r bar, and here we have on top some background matrix, rho and sigma. And then there is another part which is has a slightly more complicated structure in terms of derivatives. So we have here this term, and then G bar mu d bar rho d bar sigma plus 2 1 over 1 minus 1 over alpha G bar mu rho d no d sigma, and finally everything is packed and closed by this H rho sigma. And now you see the bad part to invert would be this, because this has comes with open derivatives that are not packed into Laplacians, background Laplacians, and therefore this would, it's not that one cannot do the calculation with this, it's just that it is more annoying. But we can use, and here to answer your question, we see that explicitly that in harmonic gauge. So if one sets alpha equal to beta equal to 1, these terms drop out, right? Because this one is 1 minus 1, and yes, also this one vanishes. So in
what is C for indices?
Yeah, in the square parentheses,
There's a C
you have
for indices.
the
Like
bar
that,
tensor.
yeah, then yeah, there must be.
I think there's a plus or minus missing in front of the bracket after.
Oh yeah.
Yeah.
Yes. Probably is something, I don't know.
No.
In my notes,
After C, there's either a plus or a minus, and
okay. Okay, this might be. I in my notes is probably wrong. So I don't know if you have that in the lecture notes.
It's a minus.
There is a minus. Okay, sorry. And thanks for spotting the typo. Yeah. Okay. Yeah. So so the point is here I'm already writing stuff in terms of dimensionless. Well, they are related. So the G K is the dimensionless Newton coupling, which in 4 dimension is the big G, which has dimension m2 - 2 times k squared. Yeah, sorry for skipping this. In general, one has to work with dimensionless coupling, but in principle, one can keep the dimensionful one till the end and then replace. Yeah. And at this point, so 25 minutes left. Okay, then let's be done. Yes, so at this point, all of this stuff can be repacked in a very nice form, thanks to spins projector. So essentially splitting our H field in traceless and trace part. So all of these once again can be written as and the inharmonic gauge. Otherwise, one cannot really do this splitting so easily. And here we have this delta plus 2 over 3 r bar minus 2 c, which is essentially the contraction of the c bar with the matrix, minus 2 lambda k, and the spin project, which is the traceless part. And we will call all of these delta 2, and this is what we will use for the regulator function, minus delta bar minus 2 lambda k, and then the trace part of the spin projector. And this type of splitting helps because then at the level of the inversion that appears in the right-hand side of the matrix question, one can essentially invert these single scalar parts, almost scalar parts, because the two do not talk to each other. They are completely decoupled. So the trace part and the traceless part in harmonic gauge are completely separated. So now I can actually just give these two part to the heat kernel formulas. So just inserting these parts. Regulated ones, actually. So one has to add to the quadratic part the regulator for the gravitational contributions individually, because they now have the structure. So the gamma 2 H now would be of the form 0, 0, and then so this is exactly what this means. This is the trace part and the traceless. And therefore we can just regularize them individually, so adding a regulator. And the same then would appear in the KDK RK. And in particular, as a regulator, now we can do the following. So we have this delta SK for the graviton part, which is 1 over 32 pi GK. So once again, we use the same prefactor such that the things cancel out. And then here we have the H window and the regulator part for the traceless part of the inverse propagator. And in particular, this term, now for this term, we can use the same trick that we used before. So the type 2 regulator, I pack the endomorphism inside of the regulator. This is the type 1. And I called this delta 2. So this delta 2 exactly goes inside here. And we have once again the projector. And this is for the gravity part. And we have something similar now for did I write that? Yes. There we have also this delta, and this is also actually completed on the background. And now you will see that here, aside from the spring projector, and here let me reclose this. So this would be rho sigma, and all of this as indices mu rho sigma. And in the regulator, I'm only including the Laplacian bar and this delta 2 bar. Actually, here I made a mistake. This only includes up to C. And not the cosmological constant, because the cosmological constant essentially has the mass dimension of the cosmological constant is m squared, so essentially it's a mass term. And if one includes the mass term in the regulator, one is ruining one of the properties that we need to preserve. So the fact that in the limit k goes to 0, the regulator goes to 0. And if there is a cosmological constant, even if it is small at low energies, in principle can ruin this property. So we need to have the cosmological constant outside of the regulator. And this has to be added to the quadratic part of the action. And once again, then we will have now functions of this delta bar 2 and Laplacian on the background, and we can apply the formulas of the kernel techniques. Okay. Technically, once we do this, we will end up with a structure that is very similar to this. And I think it doesn't really make sense that I write it down like the right-hand side of the flow equation for the gravitational part, because structurally is essentially like this. So there is no difference. There will be like different numbers there. But the same type of integrals, exactly because we use that formula. So what will happen is that since this the gravitational part comes, of course, from a spin to field, then there will be some extra factors that then change a little bit the formulas, and we will not have enough, and we will have the regulator for the gravitational part, but structurally they are exactly the same. And then they sum up, and they give a structure like this. So now the right-hand side will really have that form. And in order to compute the threshold integrals, the only thing left is to specify the regulator. The regulated shape function, this RK of Z, both for the gravitational part and the ghost part, and typically one choose the same. And the one that one can choose typically is the lithium regulator that Benny told you about. And specifically, I didn't write it down, but this has the form y minus z, then the theta function 1 minus z, okay? And once this is specified, one can perform the threshold integrals and obtain exactly something like this. So the right-hand side would have this form. What we need to do finally is to compute the left-hand side of the flow equation. but the gamma k is just 1 over, let me write this way, so we have an integral over space-time, and then we have 2 lambda k minus r bar, because now we are computing stuff on the background, so at 0 fluctuations, and the 16 pi gk. So when I hit the effective average action with the k decay, what do I obtain? I obtain this term here, and then here I will have 16 pi gk square, and then gk that multiplies 2k dk lambda k plus, no, minus k dk gk times 2 lambda k minus r bar, yes. And now, once again, we can rewrite this stuff as an expansion in r bar. And then what we obtain is gk times gk k dk lambda k, and then we have also this part minus 2 lambda k dk g k over 16 pi gk square with some cancellation that can happen, plus then we have the only part that remains is the one proportional to r bar, and this only leads to something like this. So, yes, I think this should be it. And now what do we have? We have a function, r bar, a function. On the right hand side, we will have a space-time integral, a function plus r bar, another function. We can compare the two and equate this one with this, and this with the second one. And we have finally our beta functions with just one little effort more, namely we have to replace this gk with k square, and then our little g, and here we do something similar for the cosmological constant, and then take into account that the beta functions by definition, so the beta g would be k dk gk, the beta lambda is k dk lambda little lambda k. So we can insert everything in there, compare, extract the beta functions.
Sorry, just
Mhm.
wasn't the opposite that? Small g is g times k, right?
Yes, sorry, because this is mass to -1, -2. So this is -2 and this is +2. Thank you. Okay, and at this point I can could write down the beta functions, although not much can be learned by just looking at them. Well, they are short, just quickly. Finally, after 4 lectures of introduction to concept and stuff, we can write down the beta functions for the simplest possible case. Beta g, which is 2g 1 minus g 23 minus 20 lambda. All of these are gk, but it's just a shortcut. And then we have 6 pi 1 minus 2 lambda plus g minus g plus 5 lambda. And beta lambda now is -4 plus beta g, just replacing over g lambda plus 5 g, not 59, 12 pi 8 minus beta g over g, 1 minus 2 lambda minus 7 g 3 pi, and 1 minus 1 over 14 beta g over g. Beta functions for dimensionless Newton coupling and the dimensionless cosmological constant. What do you see is that for g equal to 0, this goes to 0, and if you also set the lambda to 0, here we get something that is 0, because this makes this term vanish, this makes this term vanish. Beta is 0 for g equal to 0, and for lambda 0, this also vanishes. So fortunately, we find that the free theory is still a fixed point, okay? But if you solve these equations, just plug them in Mathematica, you see that there is another fixed point. So the result of this, if one looks for fixed points for zeros of the beta functions, one gets the important fixed points of those for that corresponds to positive Newton coupling. There is also another one, are g equal to lambda equal to 0. And then there is, this is the Gaussian fixed point, obviously. And then there is the non-Gaussian fixed point, with g that is approximately 0.54 and lambda that is approximately 0.064. And this is a non-Gaussian fixed point being at non-zero values of decoupling. And well, from the first lecture, you should remember that it is important to study the stability properties of these fixed points. So in particular, the stability matrix. The stability matrix in this case is the variation of beta g with respect to g, variation of beta g with respect to lambda, variation of beta lambda with respect to g, and the variation of beta lambda with respect to lambda, evaluated at the fixed point, at some fixed point, so g star, lambda star. And out of this, it is important to compute eigenvectors and eigenvalues. And for the Gaussian fixed point, surprise, surprise, we get the eigenvectors that are aligned with the axis, so aligned with the g and lambda. And the eigenvalues, so our minus the critical exponent, are -2 and +2. Why? Because these are the canonical mass dimension of lambda g. It makes sense. All of these closes to something nice. But then we also have this non-Gaussian fixed point, which is attractive, fully attractive in the g lambda plane. And in particular, the critical exponents 1, 2, or let's call that theta plus minus, are actually the complex conjugate. So in this case, it's something like this, plus or minus I imaginary unit 0.958. And this tells you essentially that trajectories close to the fixed point are spirals. So finally, looking at the phase diagram, based on these beta functions and these fixed points, what is the situation? What do we get? We get that there is one Gaussian fixed point and somewhere a non-Gaussian fixed point. Here, let me represent the dimensionless cosmological constant and the dimensionless g. Here we have this direction is attractive because the canonical mass dimension of lambda is +2. But the Newton coupling has negative mass dimension. So we know that from general relativity, and this is what leads to perturbative non-renormalizability. So we have that this is not fully attractive, it is a settle point. Therefore, renormalization group trajectories would do like this. And this is what we see in perturbation theory. But perturbation theory would extrapolate maybe that these trajectories go somewhere at infinity, but practically because of this additional fixed point, trajectories bend towards the UV and can reach this fixed point. And then one can have different trajectories, so different IR. This is the simplest flow diagram that one has. This is the direction towards the IR. This is, yes?
What do you mean now by IR? I mean, you're still the flow variable is still little k, right?
So now I still have little k, okay? So this is the k running.
Yeah.
And by IR, I mean the physical limit k that goes to 0, okay? The existence of this fixed point essentially tells us that I can take the continuum limit and this has our Bayer action, we have a well-defined Bayer action from which we can start from, okay? And then out of this, we can then study the landscape of effective actions that come from this, that we obtain as k that goes to 0. In particular, we could get, instead of studying all of them, we can say, well, I measure my cosmological constant, which is something small. I measure my Newton coupling is something like this. So this is my point. This is my trajectory. And from there, well, this is a pretty trivial case where the effective action is just Einstein-Hilbert with the measured values. So let me just write the Lagrangian is the Einstein-Hilbert Lagrangian with the Planck mass and the cosmological constant given by observations, because they are both relevant directions. So I do not get the predictions. In this case, I get something that I have to measure, 2 parameters, but actually 1 because we only measure dimensionless quantities. So practically, what I care about in this case is the product of G times lambda in the limit as k goes to 0. And so essentially that would select the observed value of the cosmological constant. As one goes to higher order, all of this gets much more difficult. But let me, yes. I know. So it says, what is the meaning of the poles in lambda in the flow? Don't they restrict the flow and hence the IR values of lambda? Well, we believe that that is just an artifact of how we are writing down the action. So in principle, they shouldn't be there. And if one, so I know that some people, maybe also Benjamin, is thinking about setting up on-shell flow equations, and then these problems should be should at least get, but I don't know if it is completely cured. But I don't think they have any physical meaning for sure. Also because lambda does not run in a physical space, so it is just an issue of truncating and probably not expanding around the physical backgrounds. Okay, and I hope that answered partially at least the questions. We don't have a full answer to that. But now, okay, I have shown you Einstein-Hilbert, and then you may say, okay, but that's easy, that's too restrictive. It is true. However, well, the literature is full of these functional normalization group calculations in hundreds of different approximations. So let's see what's beyond what we have seen in these lectures. First, FRG calculations beyond Einstein-Hilbert. There is a lot that has been done from simple truncations. Simple truncations like r plus r square literally reaches scalar, and here a fixed point is found, and something like, look at all of them, r mu square plus r mu sigma rho square. And here we have, we see there is an Gaussian fixed point. F of r truncations, like without even expanding about r equal to 0, has been done. So literally looking at dependence on k of this function. And here we also see fixed functions. And also expansions of this type. So f of r truncated to some order has been done. So something like this with coefficients to order n, and I think beta functions have been computed at least like until n equal to 71, was it? Something like that.
Does the location of the Mies function converge as you?
Yes, exactly. So in studies like this, one sees that, the fixed point values actually is not something physical. You also would see that from condensed matter physics. So it's not the values of couplings is not really something physical, but the critical exponents should converge. And in this type of calculations, one sees that as one goes up in the truncation order, things converge. There is at least apparent convergence. So this is what we can see. Very importantly, there was a work done by some people in the community, including Benjamin, showing that the Gorov-Sagnotti term, so just Einstein-Hilbert plus the Gorov-Sagnotti term, is asymptotically safe. And this was important because was extremely important. This physical variable letters, because the Gorov-Sagnotti term was the one that within the context of perturbative quantum gravity signaled that it was impossible to have essentially a perturbative renormalizability of gravity with respect to starting from Einstein-Hilbert as a very action. It was a game over. And this was shown to be asymptotically safe. And there are also variations of this. And in particular, one thing that is important is that Einstein-Hilbert has been also tested together with matter. And one can see that if matter is something like the standard model, plus or minus a little bit of stuff, we still have the fixed point, which is good. But too much stuff is not good, because too much stuff. If we throw like 100 vector fields and 100 scalar fields, then we lose the fixed point. And this means that all of these setup, if it works, has also predictive power, in the sense that it doesn't work with everything, with any matter. You have a question?
Yeah. When you say fixed point, do you mean a fully attractive fixed point?
No.
Partially.
And it is partially attractive, and it would be bad if it would be fully attractive, because it means that we have zero predictivity. And instead it is, so if you have a fixed point which is only a few relevant directions, so a few attractive directions, then it means that you have to compute, you have to experimentally fix a couple of parameters, and all of the rest that appear in your effective field theory are fixed are computable by the theory.
But it could also mean that you are just not living on that hyperplane, and then you.
But then you are not asymptotically safe. It means that you need either there is another fixed point, or then you cannot rely on the quantum field theory for sure, just based on the fixed points. And going in the direction of predictivity and consistency, I will tell you a couple of more things, and then we switch to the gong show, but I care about saying something about predictivity, which is something very interesting in asymptotic safety. So aside from the whole framework that allows to compute the parameters, and of course, the framework is nice, at least in my opinion, it could be realized by nature or not. We don't know, of course, if asymptotic safety is there in nature, but it is important to understand whether we can make predictions, we can falsify stuff. And at least within like simple approximations, so there is something very nice which has been done, which is the prediction of the X mass at approximately 126 GeV, and this was done by Shaposhnikov and Vetterick in, I believe, 2009. That means like a couple of years before the discovery of the detection of the Higgs boson at the LHC. And also using these coupled gravity matter systems, one can also postdiction of the top mass once the Higgs mass is fixed. So actually what one computes is the ratio of the two, but so this is consistent with of course consider these are like rough approximations and still getting a value which is that close to the actual measured masses is non-trivial. So I mean, even if asymptotic safety perhaps is not fundamentally realized by nature, maybe something is going on here that is non-trivial. And there is also a possible mechanism to make the standard model asymptotically safe, and therefore in practice to remove Landau poles from the standard model. And this is really about coupling gravity with matter, because then gravity looks enter matter couplings, the running of matter couplings and vice versa. And this can create additional fixed points that then remove divergences at higher energies. This is like the packed information. And in terms of consistency, well, there is still obviously a lot to do, but especially recently, some progress has been done, like to start testing whether asymptotic safety can be unitary. And there are works providing proof of principles that asymptotic safety amplitudes, asymptotically safe amplitudes can respect the positivity bounds. There are arguments that if one truncates the action, there can be fictitious ghost, but as one increases the truncation order, this decouple. So one should not just worry right away. One should try to compute amplitudes and with a decent truncation order and see. And there has been also some works that include Lorentzian signature and compute the graviton propagator, showing that at least in this in a first setup, it seems like there are no ghosts, no additional degrees of freedom in the propagator. So it's a first step. I mean, it's not the end of the story. A lot has to be done still, but it's a good starting point. And of course, there are a bunch of open questions. Some of them we have already discussed, like understanding diffeomorphism, the recovery of diffeomorphism invariance as k goes to 0, and obviously more has to be done regarding unitarity, or more generally computing amplitudes in asymptotic safety. have these truncations under control, or try to understand if we can make statements that are independent of the specific truncation. Well, this is let me add also one personal wish to the list of asymptotic safety, that is understanding black holes in asymptotic safety. How do they look like in this framework? And yeah, with this, I'm sorry that I'm a little bit late, but thanks for following. And yeah, if you have questions, you have yeah, and now, yes.
Dilaton gravity is included?
So I think there are also some works in that direction, but now I cannot remember. I mean, there are in general works on the scar tensor gravity, and also recently on Nasty gravity, and typically there is a fixed point. Yeah, but I don't remember how much goes in that direction.
Can you say something on the neutrino?
Well, probably there is some work, but it was not very extensive, at least that I remember. Maybe Benjamin, I don't know if you remember something. But I mean, I think that there is some work by Masatoshi Yamada in that direction, also checking like whether asymptotic safety can say something about Derek versus Majorana Fermons, but now I cannot really remember the punchline. So my guess is that maybe it was not very sharp, so that it really it was something that everyone had to study. But yeah, maybe some work in the direction is being done as well.
I would say it's a second order problem. We first want to get like the main parts of the standard model.
Yeah, that for sure.
Like, you know, QCD and Landau pose. That's kind of the first issue.
And yeah, there is actually an extensive work about the asymptotically safe.
The standard model is not correct because the neutrino has a mass.
Yeah. Are there online questions? No. Okay, that's good. But then I think we should, if there are no urgent questions, you can ask me later, and we can switch to the gong show such that we can at some point go for lunch.
Let's thank Alessia again.
Thank you.